Okay, let's continue. Now I'm gonna go into deadlock avoidance. So far we talked about deadlock the prevention. Prevention means you want to make it strict so that deadlock cannot happen, right? By breaking one of the four necessary conditions. Avoidance is probably the more useful and practical model, but it does need a priori knowledge about the system. So that means things like each process needs to do some declaration and say what's the maximum number of resources of each type it may request. So for example, can it ever use how much memory, and can it ever use certain devices? So like modern smartphones might even say, do you want to allow it to use, say, your Wi-Fi or Bluetooth, your location service, right? These are all resources. So that means that these are what's called a priori knowledge. And then once the system has the maximum possible request of each resource type, then it can do something by running certain deadlock avoidance algorithms. So what do these do? Well, these algorithms will dynamically examine the resource allocation state so that as additional requests come in, it can at least check, okay, how far am I from the maximum request? And is there going to be sufficient? Is it okay for me to continue requesting? Because these are kind of like the promises. Say, I promise not to request more than this much, and the system is going to hold you to it. And so if you try to request more than you promise, then the system may just stop you, right? And at least system can catch you. But that's useful because that's useful for it to kind of come up with a budget, so to speak, and also the sequence in which it can really avoid deadlock. And so resource allocation state is defined by number of available resource instances and allocated instances, and the maximum demands of each process. So that's a promise made by each process. And here's a concept of what's called safe state. A safe state, a system is in safe state if there is a sequence of process P1 through Pn, such that when P1 requests resources, that's equal to current available plus those held by others. So that allows the OS to decide if a particular allocation leaves a system in a safe state. Okay. So here, if process PI it has certain resource needs, but it has to wait. Then it has to wait for the other ones holding those resources requesting. And when P sub j is finished, P sub I can obtain the needed resource, execute, and then return. So what it does is it hopes that you can find a sequence such that even if you wait, you order it such that the ones you ordered before will give back enough resources for the blocked ones to fulfill its request. Then you can continue, and then everybody can finish. Okay, so that's really the whole point. So in the safe state just means that sequence of ordering the processes exists so that you enable these everybody's request to be satisfied, but only in a certain sequence. Okay, and then so there's an algorithm for doing that. So, but system is in a safe state, then there's no deadlock. That's kind of by definition. If system is in unsafe state, again, it's a possibility of deadlock, but does not imply definite deadlock. So avoidance means it's to ensure system will never enter an unsafe state. So really, so here is more of an illustration. Deadlock is a subset of this unsafe state. Okay. Now, there's different deadlock avoidance algorithms. One is if you're assuming each resource type has only one single instance. And the other is you can, for each resource type, you can have multiple instances, and they are all considered equivalent. Okay? And so if you assume only one resource instance per type, then you can use the resource allocation graph for that. And we saw an example of that earlier. If you allow multiple instances per resource type, then what's called a banker's algorithm can be used. Both require a priori knowledge about resource needs. And these are called claims. Okay, so in the first case, you assume only one instance per resource type. Then you can construct that resource allocation graph. And we've seen a version of it. A claim edge means you may request. Okay, so it's an edge from a process to a resource. And so that means, well, how do you make request? Well, the programmer has to tell you that. Request edge, that means it's actually making the request. So the code comes and executes the actual wait, right? And so then it's requesting a resource. And so that's when the claim edge, which is just the potential, gets converted into a solid edge, right? The claim is just a may request, so that was a dashed line, turns into a solid line. And so that means the process is waiting for resource RJ, and it's just one instance. Assignment is the other direction, right? So it goes from a resource to a process. And so when the resource is allocated, you can say once it gets past that wait statement, now it's in the critical section, then you essentially flip the direction, right? Then the request now becomes assignment, so in the opposite direction. So it goes from resource to process. And then when it's done, then flips back and then converts it from solid line to a dashed line. So that's how the resource allocation graph data structure works. And so here you have an example. So assignment of R1 to P1. P1 claims, so that means it may, right, and may make a request. P2 also does a claim, which means it may request. And P2 does a request. And so as your processes are running, then this resource allocation graph gets maintained and updated, okay? And so what would be an unsafe state, right? So if there is, now you see a cycle, and that actually includes a claim there, right? Claim is in the same direction as request. So if there is a cycle, then that means it is in an unsafe state. So request will be granted only if no cycle is created, okay? And because the assignment request edges can flip back and forth in directions. So, and to do this, worst case would be n squared time. And as you know, in OS, anything more than log time is very expensive. Linear time is like, forever. N squared, that's horror story, right? So it's not thinkable on a regular basis. But what do people do? Then they could sample it, okay? Or you limit it to a small number of n, right? So in this case, right, so then, right, so this data structure is maintained to avoid entering unsafe state. So request can be granted only if converting request edge to assignment edge does not result in a cycle, right? So request, if it converts to assignment, does not result in cycle, then it could be requested. The request be granted. Now, this concept of safe state can be extended to multiple instances per resource. And so what this does then is it will need to compute whether there exists a safe sequence. A safe sequence is one such that you can unblock processes, right, in a particular order, or you assign resources, and then when they finish, you unblock, they allow other processes to fulfill their request in a particular sequence. So in some sequences, they might not be fulfilled, but in other sequences, just as long as there exists one such sequence called safe sequence, then it's considered to be in safe state. Okay. So now here is an example. Processes P0, P1, P2 make the promises that the max needed will be 10 and 4 and 9 of some resource, right? And then currently P0 may be holding 5 instances, P1 may be holding 2 instances, and P2 may be holding 2 instances of that resource. And then, of course, you can have multiple types. Right now, we're just showing one type, one resource type. And so when you're in this particular configuration, does there exist a safe sequence? Well, so, right, so here, let's take a look, right? So now if we do, well, after running the algorithm, you find and P1 first and then P0 and P2, that is a safe sequence. So let's see. So P1 currently holding 4, and then it needs, so it's currently holding 2, and it may need up to 4. So it has 4. So if you allow P1 to do, worst case is it grabs all the resources it wants, right? So currently holding 2, max is 4, so that means in worst case it grabs 2 more. And that's makes it 4. So P1 can continue. Now, after P1 finishes, you get all 4 units back. So that's actually a good thing, right? So you don't just think, how much do I spend allocating, you want to think in terms of how much you can get back based on this current holding as well, okay? So once you, right, available maybe 3. So worst case, it gets 2 and there's still 1 instance left, okay? Now, but then after P1 finishes, then it gives back all 4 instances. So your available used to be 3 down to 1. Now you add 4 back, it's 5, okay? And that helps a lot because then you have total of 12 drives, and now available was 5 before. And now if we execute P0, well, it's currently holding 5. There was 5 available, so we give all 5 to P0, and it's maxed out at 10. And there's no available drives at this point. But is that okay? Yes, it's okay because P0 can execute till completion and release all 10. And that helps a lot because now when P0 finishes, it gives back all 10 and then it's done. And then if we execute P2, well, it's currently holding 2. The worst case is it requests 7 more, right? Because the max is 9. But we already, but at the time P0 finished, we have 10. So that's more than enough to fulfill the worst case request for P2. Okay, so
why
minus 9 because P2 has the, oh, you're right, it should be 7. Good checking. Right, so that should be 7 because it's holding 2 and then 7 got allocated to it. Thank you. So it was 10 available minus 7, so you still have 3. Okay, so then they all execute. Okay, so this just goes to show that you don't necessarily want to grant these requests in first out order, or not even priority order. You want to consider the requests as well as the current resource allocation in order to make a decision, to find a safe sequence so that no deadlock. Okay, so
what happens if you know in a theory that you have a maximum promise of resource, and you hold in a specific number of resource, but there is no any safe sequence?
Then you may get into deadlock.
But it's like you are running in a specific process, and you already know that you will get a deadlock. What's the procedure?
No, so deadlock requires all 4 necessary conditions to hold, and you would have to do a much more careful analysis of each process where they are, right? And but it's here. This is that picture. Remember that picture? Just because you're in unsafe state doesn't mean you'll get a deadlock. Only if you're really, really unlucky, then you get a deadlock. Okay. Most of the time, even if you go into unsafe state, you're probably not that unlucky. It's just okay, goes through, and you're okay. Yeah. Okay. So now there's this other. So this is unsafe state without. So that means that there's no safe sequence. And so that would be an example. So still 12 drives, and at some time, so P0, P1, P2 still makes the promises of making like max of 10, 4, and 9, currently holding 5, 2. But instead of 2, which was the previous, right, it's now holding 3. And then available is 2, right, because 5 plus 2 is 7, 7 plus 3 is 10, so 12 minus 10 is 2, so only 2 available instead of 3. Now if P2 allocates one more drive, because, okay, look, this is the worst case we're talking about here, okay? The max is just the worst case. So just because it says max is 9, is it going to allocate all 9? Or just because it's currently, right? Right, it's holding 3. Is it really going to allocate 6 more? Not necessarily. That's just a worst case. So worst case, yes, you actually are much more likely to get into deadlock. But if you allocate less than your worst case, yes, that may put you into unsafe state. That doesn't mean you automatically deadlock. Okay, so now you're holding 3 here, and then you allocate 1 more. What happens? So that brings available down to 1. You're holding 3 plus 1 equals 4. Okay, and then there's no safe sequence because remaining 1 drive cannot satisfy any other process. So because all of them may need 1 more drive. And so this system enters unsafe state. So now how can you then use this to as an algorithm for the deadlock avoidance? Then, well, Banker's algorithm. It's a way to track multiple resource types and instances. And of course, you need a priori claim for maximum use. And the Banker's algorithm it uses a general safety algorithm to predetermine if any safe sequence exists after allocation. And the safety algorithm is really to find a process that can be satisfied by freeing its resource. Well, because satisfying it allows you to go ahead, and then that's another way of viewing it is to free the resources already assigned to that, right? And you have a lot more to gain, and then you can use the freed resources to see if you can satisfy other processes in a different sequence. And then, or in a subsequent sequence. So then the banker's algorithm uses safety algorithm to determine if a safety sequence exists. If so, it allocates only if a safety sequence exists. Okay. So to explain banker's algorithm, you need to know a few variables. Now these may be slightly confusing because they're somewhat more condensed or more terse than they really are. So you need to know what they really mean. So by convention, N is the number of processes and M is the number of resources. Okay, and this is going to come back multiple times. And then there's an array, int array called available of M. Okay, and so that means it's the number of instances of each type that's available. Okay, so that's why dimension is M. And work is also M-dimensional. So it's the number of resources. It's the number of instances of a particular resource type that not yet allocated. And so then max is equal to, well, max is really a two-dimensional array. So that is a promise. So by each process, which is N, right? And then saying how many instances of a particular resource type it may request in the worst case, right? So that's M. So it's a matrix, right? Each process has such a vector. Now allocation, it's also two-dimensional, and it's now what it's tracking is that process P sub I is currently allocated these a certain number of instances of particular resource type. Okay, and there's need, which is also a two-dimensional array, and so this says P sub I may need up to this matrix entry more instances of R sub j to complete this task. So you can derive need from subtracting max of ij, so max of ij minus allocation of ij, right? Because max is the worst case request, and allocation is currently already allocated or assigned to that particular process and each resource type. The need is just how much more to the worst case, right? And the safety algorithm works like this. So now I use slightly different syntax from the book because the book is just using pseudocode, and when you do assignment, especially when array, that's, well, they just think it's it's copying. But for now, I wanted to make it a little bit more explicit, so I make it. I mix a little C syntax with Python syntax. Okay, so first, work of M gets available everything. Right, so this is the entire slice. So you just and then so actually it's the entire. Okay, so here. Right, so they are the same. So this is really the C declaration, and that's more Python. Okay, and then Boolean finish. Okay, there's a separate array of Boolean that's all initialized to false. Okay, and so finish just is tracking, have I already fulfilled the requests for a particular process in this particular snapshot? Okay. And or have already defined a place for it in the sequence. Now, what the safety algorithm does is it iterates over these processes to find I, which is an index into a process, such that it hasn't finished yet. In other words, it's still waiting for resources to be allocated to it. So so that means finish sub I equals false. So I is a process index, and its needs of different resources is less than equal to this work vector, which is really a copy of available, right? So if it hasn't finished and its worst request is no more than what is currently available, right? Then yes, that is an I that I want. Why? Because that means I can go ahead and schedule it and satisfy all its requests. And then after I schedule it, I can free up its resources, right? So then, so to find that I, and then it will continue. But if you can't find such I, then you break out of the loop. So 1 is just before the loop. 2 and 3 are part of the same loop. 4 is after the loop. And if you break out of the loop, that means you can't find any process that either hasn't finished or it hasn't finished but at the same time its resource needs cannot be satisfied. Then you break out of it, right? So if everybody's already finished, that means great. We've already found the safe sequence. Otherwise, it's in an unsafe state. Now, if such a process can be found, that means you can fulfill its request with the remaining resources that haven't been assigned. Then, well, we just found that it can be fulfilled using current resource. So finish sub I gets true. And after we run it, guess what? We get the allocation back to the pool, right? So that means work gets work as a vector plus the allocation that was allocated to I because we just finished it. Okay? So allocation two-dimensional, that and they put the I dimension for that process as a little suffix as opposed to another bracket. And all of its resources back. Add them back into the work pool. So here, that's why it may be slightly confusing because you don't take it from the work pool. Yes, you actually gave it to the process, but then after it finishes, it already comes back. So you don't need to subtract and then add it back again. In fact, when you add, you even add back the other previously allocated ones to it. All right. So then loop again, find the next one. Because it's already finished, then anytime you try to iterate over this, the A2.A will fail, right? And then it just keeps looping. So you can imagine this as two nested loops. One is outer loop, and then one is the inner loop. Number 2 here is already an inner loop, and then 2 and 3 together are in an outer loop. Okay, so it seems pretty simple. Yeah.
In the number 2, when we are finding a process that has a need of resource and they have a viable resource, what happens if we find several processes that they fulfill this condition? Number 2.
Yeah.
Which one we are taking?
So this doesn't specify. This just says you find an I. Just as far as this is concerned, it's as good as any. Okay. So here's an example. In this case, you have 5 processes, P0 through P4, and there are 3 resource types, A, B, C. And A has a total of 10 instances, B has 5 instances, C has 7 instances. And then each one has its max, which was the claim, right? So worst case, P0 may use 7 instances of A, 5 instances of B, 3 instances of C. P1 may use 322, P2 may use 902, and so forth. Now, allocation is at this point in time what's already assigned. So as you can see here, it doesn't require you to make all your resource requests in all one shot, and you only get one chance, right? So you can make requests, and then as you need, make more requests before you release the other ones. Okay. So then need is derived from max as a vector minus allocation as a vector, right? So this minus that equals need. So 7 minus 0 is 7, 5 minus 1 equals 4, 3 minus 0 is 3. So that's how you get this column here. And then available, right? So that was also done in, so it was initially 10, 5, 7, right? And then what do you have to do to calculate available? Well, so what you do is you add up the allocation in columns, right? So A already got allocated 2 instances to P1, 3 instances to P2, 2 instances to P3. So if you add them up, 2 plus 3 plus 2, that's 7 instances already allocated. That means available is 10 minus 7 equals 3. Okay, so that's how you derive these. So book doesn't always explain clearly, but that's what it is. Okay, and this is just a snapshot in time. And to run the safety algorithm, we'll first initialize. There's 3 resource types. N is 5 processes, right? So work gets initialized to available, which is the value 332, right? And that's what we derived here by taking total available for each type minus the total allocation for each type. Right? The 322 comes from here. So 322, that's work and available. And finish is just all false. Now you enter, there is an outer loop and inner loop. And so the so let's just consider for I equals 0 up to 4, and then you keep iterating. Now need of 0 is what? Well, need is that. We already did a subtraction here, right? Max minus allocate. So 743. Now you do comparison. Is 743 less than equal to work, which is 332? And the way you compare is 7 less than equal to 3. Is that true? 4 less than equal to 3. Is that true? Or 3 less than equal to 2. Is that true? Well, no, because as soon as you have one of them that is not true, then the whole comparison fails, right? So so 7, because 7 is not less than equal to 3. 7 is greater than 3. So this comparison fails. So you do the vector comparison, so pairwise. It's not lexicographical. It's just pairwise, and you have to AND them, okay? And so that's false. And also finish is false. So that means, P0 was waiting, still has to wait, okay? Because right now, I don't have enough available, or work, really. Work is a copy available to fulfill all its requests. Well, I mean, that doesn't mean you couldn't go ahead and run it and be okay, because we're doing the worst case, okay? It may actually allocate less than your worst case, which may just run fine. But we're being conservative here, okay? We take the worst case. Now next step, okay? I was 0, couldn't do it. Now try I equals 1. Next process, it's need 1, 2, 2, and you can figure out from the previous table. Is it finish? No, finish sub 1 is false. Okay, then we check the next condition. Need sub 1 is less than equal to 3. Work, which is 332. So 1 is less than 3, correct. 2 less than equal to 3, yes. 2 less than equal to 2. Yes, this is one we can go ahead and run. So that means we add it to the save sequence. So P1, we mark it true, right? And then So we mark finish to be true. But before, when it's finished, then what do we do? Well, basically we add any resource allocation back to work, right? Because allocation means we assigned it, but the process finished. It has to give us the resources back. Now it was allocated 200, so we add that back to work. So now work becomes 3 plus 2 is 5, 3 plus 0 is 3, 2 plus 0 is 2. So work now, by scheduling P1, we actually get more resources back. Yes, we have chance to fulfill more requests. Which one? Right, so that means the resources of each type, resource 0, resource 1, resource 2, I already allocated. This is a snapshot. Okay, so there is some other thing before, we don't care. This is an instance where this safety algorithm kicks in and tries to check. Okay. And now step 2, we consider process I2. And its need is 600. Now work is 532 as updated earlier, right? So is it less than or equal to 532? Well, no, because 6 is not less than or equal to 5. So that evaluates to false. Finish 2 is false. You can't fulfill its worst case request. So let's not try it. Let's not risk it. Okay? So P2 must wait. Now let's try process 3. It has need of 011. Is it less than or equal to 532? Yes, 0 less than 5, 1 less than 3, 1 less than 2. So, and it hasn't finished, so let's grab it. So let's add it to that sequence. So now we scheduled P1 and then P3, right? And then its resource allocation gets added back to work. So as you can see, work just gets increasing because as you schedule, you get more resources back. Well, it actually decreases temporarily because if you just don't see that, it's a little glitch, right? The work actually gets subtracted to run that process, but then you get those back anyway. So in this algorithm, work only increases, but in the middle, work actually decreases to run that process you just picked, and then increases back, and then you add its allocation back, right? So now you add it back, 5 plus 2, 7, 3 plus 1, 4, 2 plus 1, 3. So now we mark it true. Okay, you just keep going. I equals 4, is it less than or equal to work? So this 4 is less than 7, 3 less than 4, 1 less than 3. So yeah, as you increase work, it's supposed to be easier and easier to fulfill all the other requests. So true, yes, add it into sequence, and then that becomes marked true. So then we have the sequence of 1, 3, 4. Now, well, then we loop back to 0 again, right? 0 failed in the first place. Process 0, so I equals 0 again. Let's try it again to see. Previously we didn't have enough work. Now we have more work instances. So need still 734. Is it less than or equal to 745? No, 743, and is it less than 745? Yes, we're lucky. 7 less than or equal to 7. That's the equality saves us. 4 less than or equal to 4. 3 less than 5. Yes. So we can add that to sequence. It had the allocation of 0, 1, 0, so add that back, so work becomes 7, 5, 5. Okay. Now, if we go to I equals 1, well, we already picked 1, no need to run it again. Okay. And I equals 2 again, then need is 600, that's the worst case. Is it less than or equal to 755? Yes, it is, because 6 is less than or equal to 7, and then 0, of course, less than or equal to 5. So then we finally get all our resources back. So the sequence is process 1, process 3, process 4, and then process 0 followed by process 2. That's a safety sequence. Okay? And so usually you don't really need up to n squared time. You can imagine doing this in probably 2n, 3n tops. There's clever ways you can even avoid having to keep testing finish equal to true or false. Okay, so now to incorporate this into the resource request algorithm, so this is where an OS is in charge, and there's requests coming in. Do I want to assign or do what, right? So now you have the request I, which is the request vector for process I, and then request I sub j, which means that I wants that instance. I mean, you can call it k instances of a resource j, right? That's the request. So this is the actual request as opposed to the worst case analysis, which is what we were doing for the safety. Now, so algorithm outcome is that either safe or unsafe. So this resource request algorithm simply calls the analysis we did earlier, right? That whole safety sequence, and it gives you safe or unsafe. If safe, go ahead, allocate the request, fulfill their request. If unsafe, then this is a higher level that tries and see and make it wait, and then use the older resource allocation state. Okay. And so here, if request sub I is greater than equal to the need for the vector comparison, right? What does that mean? That means this promise, they didn't stick to their promise. They promised they never exceeded this much, right? But then now they're requesting more than they promised, their max request. So that is, so you raise an exception or raise an error condition and tell them, sorry, you broke your promise. You said only 10 drives, now you're requesting 12. No, not going to allow it. Okay, so that's one way the system can enforce this. And if now request sub I is greater than available, now that's different from need, okay? Then that means P sub I must wait, okay? And so then, just because it's not available doesn't mean it won't become available. By running some other processes, they'll free up the resources, then I check again and it'll be available. The first is really just to say, hey, you promised something, and then I did all this analysis based on your promise, but now you're breaking your promise. You request more than, then that means my analysis was all wasted because you didn't do as you requested. So it's okay to be bad to them, throw an exception at them, right? But second is, well, okay, now I'm gonna try, and so you could wait. Maybe you won't get a deadlock if you're lucky, and so then you could pretend to allocate the requested resource to PI by modifying the state. Okay, and then so then is, well, available gets available minus request, allocation gets allocation plus the request, and then need just gets updated accordingly. Okay, so now that was deadlock avoidance, and that has a bunch of mechanisms for runtime checking before you make a you as an OS fulfill a request. Detection is that you just let them run as usual, and then you try to see if currently your processes are in a deadlock. How do you detect that? So that means there needs to be a data structure called wait for graph. And as with any graph, you have vertices and edges. So vertices represent processes. And then there is an edge from PI to PJ if PI is waiting for PJ to release the resource it needs. And now, so for deadlock detection, you really have to do sampling, right? So you don't do this every single step, every time the resource gets assigned or freed. No, you actually schedule once in a while and then run this graph. Why? Because it's n squared complexity. You can't afford to do that too often. Okay, once in a while is okay. Right? And also the system gets arbitrarily complex. So periodically invoke this algorithm to check if there's a cycle. Now, if there's a cycle, what does that mean? Is it possibility of deadlock? No, there's definitely a deadlock in this case. Okay, that's the difference with the this wait-for graph, because it's actually checking who's waiting for what, and also taking into account what state they are in. So resource allocation graph and wait-for graph. Right? So resource allocation graph, well, that was only for single instance per resource type. It doesn't work for multi-instance. Now, wait-for graph you can think of as kind of a condensed version, because if it's single instance, then that means only one edge from P to R, and then that R assignment to another, right? So this graph can change at runtime, but that means there's only one single edge going from P to one R and then R to another P. So you can then kind of take away all these R's and then just have the P points to another P. Okay, so so that's what the wait-for graph is. And so you can have right, so that works only for single instance, and that's what this one is. Okay, so you can say it's derived from the resource allocation graph, but it's at runtime. Now, if in case of multiple instances per resource type, then you can't use that resource allocation graph, and you can't use that wait-for graph, because wait-for is just a simpler version of the resource allocation graph. You have to go back to that same thing as available, an allocation, and request, kind of similar to that safety one, right? So available is a vector of length m, indicates number of available resources of each type. We saw that before. Allocation, m by m matrix, defines number of resources of each type currently allocated to each process. Okay, we saw that before. Request, we saw that before. Okay, so a lot of the same variables come back again. Now, so the detection, so work and finish, you saw before. Work, initialized to available, a lot of the same. And then allocation, if for I from 1 to n, if allocation not equal to 0, finish false, and then otherwise finish true. Because then find I such that finish false, request sub I less than equal to work, right? So we've seen this before. And if you can't find one, then go to step 4. That's out of the loop. But if it's that means that this process I can be fulfilled using work, and work gets work plus allocation finish gets true, goes to step 2, loop again. Now, but if finish equals false for some I less than is greater than equal to 1, less than equal to n, what does that mean? That means there is at least one process for some I, right? For which you can successfully allocate its deadlock. So in fact, all the unfinished ones, they would have this circular dependency. They are involved in a deadlock. So that's the finish array tells you. The ones that don't finish, they're in the deadlock. Okay. And it requires order m times n squared operation to detect where the system is in deadlock state. Okay, so you can do an example of deadlock detection, but I think my time is up, so I'll let you absorb this material, try to go over this example before next lecture, and we'll go over it again next time.